we have some statements about vectors in R3, and they're all really obvious. If V is ABC, the vector ABC, then magnitude of V is the Pythagorean theorem, square root of A squared plus B squared plus C squared. A number D times V is D times ABC, which is just dA, dB, dC. If V equals vector V1, V2, V3, W is W1, W2 plus W3. And notice I went away from ABC because we're going to talk about higher dimensional vector spaces. Just tried to send you the email. Thought it had been sent and it screwed up again, but second try I think it went through. Okay. So anyhow, we're going to subscripts on our components because we're going to higher dimensional vector spaces, and we not only have to keep track of a bunch of different letters that aren't as obvious as ABC if we try to use letters of the different letters of the alphabet, but the subscripts, we can go up to any subscript. If we want to do a 42-dimensional vector, we just have to list 42 of these. Okay, and usually we won't list them, we'll think about them, but okay, so we have V and W. So V plus W is going to be what's obvious. V1 plus W1, V2 plus W2, V1 plus W3. And I think I asked everybody to submit that, and everybody got that right. And V plus 0, well, 0 vector is 0, 0, 0. When we add it to V, it doesn't change anything. So V plus a 0 vector equals V. In R4, we can do all the same stuff. We just add a fourth component to each vector. So we can add the two vectors. This plus this equals this. I'm not going to read it to you, it's obvious. C times V, well, C times the V1 through V4. You just multiply each one of these by C, and you get this vector. Pythagorean theorem extends, just as it extends from 2 dimensions to 3, it extends from 3 dimensions to 4 and more. It extends to any dimension. Now you might wonder why we talk about R4. Well, there are plenty of things that are modeled other than space, but even space needs to be modeled in 4 dimensions. Relativity theory and some of the deeper theories go into spaces of multiple dimensions, 11 dimensions, whatever. And our space is just essentially a projection of an 11-dimensional space. Okay, so that's all straightforward. Going into higher dimensions, just add components. Okay, now let's go back here and talk about linear combinations and a linear combination of a set of vectors, because that's going to be a very important idea. And we can do it in any number of dimensions, but I don't want to write out 17 equations, so I'm just going to do it in 3 dimensions. Okay, let's say that S is a set of these 3 vectors. I won't read them to you, you can see them. And we want to write this vector as a linear combination of the vectors in S. Well, that means this vector, the 1, 3, negative 2 vector, is going to have to be a linear combination of these vectors. By a linear combination, I mean a multiple of this plus a multiple of this plus a multiple of this. And of course you could, picture that if you got these 3 vectors. Of course there are 3 vectors in space, and you want to get this vector. Well, you could do a multiple of this vector and come out here till you get to the point where you can do some multiple of this vector, which better not come down there, it's not going to work. But anyhow, you do a multiple of the second vector, multiple of the third, and you get this. So we want to see what that multiple might be. Of course, we've got to see if it even can work. So our linear combination will be C1 times this, there, C2 times this, and C3 times this, there. We want to see how to write this vector as this sum and we're going to have to then solve for C1, C2, and C3. Turns out we're going to get three simultaneous equations that we can change into a matrix equation and solve using matrix methods. So, here's the equation, and we go ahead and multiply through by C1 here, C2 here, C2 here. So we get this, for example, C1 times 1, 2, 3 is C1, 2, C1, 3, C1. And then we get this and this when we multiply this vector by C2 and this vector by C3. So there it is, very straightforward. And then we add. Okay, well, we got C1, 2C2, and 3C3 for the first component, so there it is. C1 plus 2C2 plus 3C3. Second component is 2C1 plus 3C2 plus 5C3. 2C1 plus 3C2 plus 5C3. Third component is 3C1 minus C2 plus 2C3. And there that is. Okay, well, that's straightforward enough. There's not much to writing that out. So we make sure we understand that, and then we move on and see what we can do with that. Well, okay, before I go to the next board, I guess I better say that, okay, well, so this 1, 3, negative 2 equals this vector, which means that 1 has to equal this. Well, there's an equation. C1 plus 2C2 plus C3, C3 equals 1. This equals 1. And then this, your second component, has to equal the second component here, which is 3. And this, your third component, has to equal your third component, which is negative 2. So we're just going to write those out as equations and go from there. Well, here we have it. Here are the three equations I claimed that we need to write. There they are. Well, these three equations can be written as a matrix equation. It's this matrix multiplied by the column vector C1, C2, C3 equals the column vector 1, 3, negative 2. We see that this works. We can check it out. If I multiply the first row 1, 2, 3 by C1, C2, C3, I get C1 plus 2C2 plus 3C3. And that is going to have to equal the first row of this column matrix, which is 1. There's our first equation. Second row times this column is got to equal 3. Second row times this column is this, and that equals 3. And the third row times this vector gives us this. There's our third equation. So this matrix equation stands for this system. Then we call this matrix A. We call this column vector X. We call this column vector B. So we can write this equation as AX equals B. We can solve that equation just by matrix methods. Multiply both sides by A inverse. You have A inverse A times X equals A inverse times B. A inverse times A is the identity. So we have identity times X equals A inverse times B. Identity times X is just X, so X equals A inverse times B. So all we have to do to solve this is find A inverse, which is just going to be a bunch of numbers in a matrix that multiplies by B, and then we know what X is. And X, of course, is C1, C2, C3. So we'll know what C1 is, what C2 is, what C3 is, so that when we add those particular multiples with C1, C2, and C3 of the vectors in set S, we get our target vector, the vector that we're trying to get. Now, there's one little fly in the ointment here. We might not be able to do it. Okay? So let's think about it. Okay, to do this, we can find A inverse. Okay, but first we'd better check to see if A inverse exists, because the inverse of this matrix might not exist. Now, you can find the inverse of this matrix by any number of methods. You can use a row reduction with an augmented matrix to build up the inverse. You can do it with cofactors and adjoints and stuff, which is really not a practical method. Adjoints are mostly for theoretical calculations and proofs and stuff. Okay, you could row reduce this down to the identity matrix and keep track of your elementary operations and use what we know about that. You know, if you multiply a row by a number, it multiplies the determinant by that number. Switch two rows, it multiplies the determinant by -1. Okay? So, and if you add a multiple of a row to another, it has no effect on the determinant. Well, we know those things. So we can do all that, any of those methods to get an inverse, and maybe we can even come up with even another way to do it. If the inverse exists, though, we can find it. But first, before we go to all that trouble, let's check and make sure the inverse exists. Well, the inverse exists as long as A is non-singular. Okay? Now think about this. Non-singular means its determinant isn't 0. Okay? Because if its determinant is 0, our row operations are never going to get us there. Might think about why that's so. Okay. Well, this is where we were when Zoom so cooperatively disappeared. We're having glitches with our network, with our internet connection at the college, I think. And Zoom is coming from the college. Okay, anyhow, determinant of A, well, that's a determinant of 1, 2, 3, 2, 3, 5, 3, -1, 2, which is then 1 times the determinant of this matrix. That's going to be 6, and 5 is 11, minus 2 times the determinant of the matrix we get, eliminating this row and column. So that's going to be 4 and -15, which is -11, right? 4, -15, yeah. And then it's going to be 3 plus the determinant of this matrix. And that's going to be -2 and -9, and that's -11. And is that working out? Well, now I'm looking at it blind. Yeah, that works. Okay, 11 plus 22 minus 33, and that's 0. Okay? So A is singular. We're never going to be able to reduce that matrix down to the identity. So the inverse doesn't exist. So we can't find a linear combination of the vectors in that set that gives us our target vector. And as a matter of fact, no matter what our target vector is, we can't solve the matrix equation no matter what we're trying to find over here. Okay? So, why is that? Well, our set of vectors was 1, 2, 3, 2, 3, 4. Did I do a negative there? No, I'm sorry, I don't have the vector. Yeah, okay. 1, 2, 3, 2, 3, -1. Looking at things sideways. And 3, 5, 2. Okay, well that's 3 vectors in 3-dimensional space. You've got 3 vectors in 3-dimensional space. In general, if you choose 3 random vectors, you could get anywhere by following multiples of those 3 vectors. Pick any point in space, start at the origin, start with some multiple of the first, some multiple of the second, and some multiple of the third, you get to that point. If they're just randomly selected. These aren't randomly selected. I selected these so that this vector is the sum of these two. Okay? Which means these two vectors form a plane So I'll make a statement here then. Okay, I'm saying that this vector and this vector define a plane through the origin. You just root both of these vectors, put their initial point at 0, and they go out from the origin in some direction. And then, using combination of these two vectors, you get to any point. You want to go out here, you go out far enough that the direction from here to there is the direction of this vector, and use the appropriate multiple. So use some multiple of this vector to get to a position where you can get there with the other vector. They're not parallel, so you can always do that to any vector in the plane. Well, since this vector is a sum of these two, it's in that plane. So, no matter where you want to go in that plane, you can get there. You get there with just two of them, or you could use either one of these and this one. Okay? Those vectors all get you to where you want to go in the plane. But they can't get you out of the plane. So if you want to find a point in space outside the plane, you're out of luck. Okay. That's what this result tells you. That's why this determinant is 0, and those are connections that we want to make a little more deeply as we get into the whole topic of vector spaces, which is the topic of Chapter 4.